So thanks for having me, Peter, and giving this talk. Like Peter said, we had a workshop that we put together at Embari last fall to get all the instrument developers together. And there's no way I can cover this information in the next 10 minutes, or even a fraction of it that we discussed in those 3 days. But I'm going to talk to you about the diversity of all the different instrumentation that's currently available, with some focus on some specific ones that are actually commercialized right now. How do I? Oh, it changed for me. So I want to start with this quote. Basically, it says that there's no single sensor or sample technology that can solve all of our problems. The future lies in finding the right combination of devices and platforms on which they are deployed to address specific use cases. And this was kind of it really resonated with me. And Chris Schollen is the one who made this comment at a Goose meeting in early 2023. And this really resonated with me in the fact that we shouldn't be working independently or siloed as instrument developers, that we need to stop banging our heads against the walls for the same problems, and that we should be reaching out to all the other developers to solve some of these issues that we're facing in the development sector. And so that was the start of this workshop, to bringing all the instrument developers together to start collaborating and generating a community and exchanging knowledge. So I want to give a little history of sampling instrumentation. Look at this timeline. Starting in 1990, think about that. That's 35 years ago, the first sampling incubation instrument with SID was developed. And the submersible incubation device and all of the instruments that you see on the green lines were particularly developed for bacteria and phytoplankton studies in situ. But that was the basis for everything that's happening now. The red dot is the Ficatella paper in 2008, and then in 2012 is the blue dot for Foote et al. Studying marine mammals. And then all the blue lines, starting with, because of Austin's work with eDNA sampler at Smith Root, sort of pioneered this eDNA era of instrumentation that's currently being developed. So I believe we're in an instrument renaissance right now. There's tons of instruments being developed all the time. I just learned about 3 new instruments in the last, I think, couple months that were being developed, and a couple of analytical instruments that are being developed. So it's constantly evolving, and I can't even keep up, and this is just one little portion of eDNA. I don't have time to cover all these instruments that were at the workshop, and this is only a portion of the instruments that were there. And so there are folks here. Alan Adams is in the back. He designs pufferfish with Aquatic Lab. Please reach out to Alan. Annette is here somewhere with Hui. She's in the back. You can talk to her for the Hui Oceanic Multisampler. Austin is up here for Smith Root. Who else? Ethan. Oh, sorry, Ethan is here with Ocean Diagnostics. And Ivory from McLean is somewhere around here too. So reach out to Ivory for McLean groups. What I'm going to focus on, or just briefly cover actually in my limited time, is the commercially available instruments, because I think this is relevant to the end users in this group. So there's 5 commercially available instruments, more or less, that I think people are interested in. First is the Smith Root Auto Sampler, and it collects, it's a surface sampler, so it's deployed terrestrially, or you can put it on a boat or pier. It collects 8 samples, fully autonomous. The Applied Genomics Insight Sampler, I don't think too many people know much about this. They're out of the UK. It's a single sample sampler, but it's depth rated to 6,000 meters. And then Ethan's instrument from Ocean Diagnostics, it's depth rated to 400 meters and collects 7 samples. And then I think Vince Sieben from Dartmouth Ocean Technologies is online watching this. He is developing the eDNA sampler, which is also commercially available, depth rated to 3,000 meters and collects 9 samples. And then one of the most promising instruments is the McLean NOC instrument, Roxy, which collects up to 60 samples and is depth rated to 6,000 meters. So that's just a quick overview of all the commercially available instruments. Oh. So there is a lot of instruments that we're looking at, and it's currently being written up into a review paper right now with an end user focus in mind. And so we're developing this paper to compile all of those different parameters into figures and tables that we think will be useful for the end user community. And so that's coming soon, hopefully in the next month or two. We should have that submitted. Like I said, these are 3 new instruments that I just learned about. So recent findings in the last couple months is the sequence DNA audit sampler. I think it's out of New Zealand. Green Eyes Observing Systems Aqua Monitor. This group is actually local somewhere, maybe in Maryland or Massachusetts. And then Fluid Ion, I think, is out of France with their deep water sampler. So it's a rapidly evolving field. I learn about these things all the time. People are developing lots of different samplers. We also talked about some analytical instrumentation and modules at our workshop. And there's a lot of different analytical systems being developed right now, from on-chip DNA extraction kits or methods out of Japan through LAMP and quantitative PCR assays. We just published a paper at Mbari using surface plasmon resonance for microsystem detection in the Great Lakes on an AUV. All of Peter's work on nanopore sequencing, and then some exciting work out of Stanford on optical sensors using nanophotonics. And this is what a lot of people are driving for right now, is uncrewed systems and eDNA samplers. And this is evolving too. I just found this paper on the mini ROV sampler a couple of weeks ago. But there's people trying to put samplers on lots of autonomous vehicles, from Roxy on AutoSub to ESPs on long-range AUVs and sail drone. But there are some important research and development gaps that I think we need to address as a community, as a developer community. We have samplers, we have analytical systems that are being developed, and we have data processing pieces, but there's no communication lines between those individual pieces. And so developing these standardized interfaces between the individual modules is super important. But also, more importantly, is designing these standard interfaces for the autonomous platforms that we're going to continue to use. Because people are going to be trying to fit these samplers on lots of different types of autonomous vehicles. We need to understand what those common interfaces are going to be, so that there's not a stop, or it's not a barrier to entry to do that type of work. Finally, there's also some research development gaps on the instrumentation side. From a sampling perspective, we need to have better validation and standards reporting. So as mentioned yesterday in a number of talks, we talked a little bit about eDNA standards and validation. Well, that's true in the instrumentation world as well. So the instrumentation community also needs to come together to develop validation protocols and standard specifications reporting, so we understand what those instruments are doing and what they're capable of. But most importantly of all, I think from my perspective, we need a community standard protocol from the end user community to benchmark and validate our instrumentation against, so that we know that that data is reliable and trustworthy. So I'm going to talk a little bit about research concepts versus practical implications. So many of the early instruments developed were based on innovative research concepts. So this illustration here is showing, was from 2013 from the ESP team. And it's basically depicting the idea of why we generated the 3rd generation ESP, was for mobile sampling applications for detecting patchiness in the ocean and using coordinated LRAVs to collect those samples. But I don't know how applicable that is to our current monitoring needs right now. So, and there's a difference there between research concepts and ideas versus actual implementation and monitoring use cases. So I think we're moving in that direction right now, from cutting edge to more transect monitoring. So this is an example of using sail drone and the ESP to collect 52 samples over 40,000 or 4,000 kilometers from San Francisco to Hawaii. And basically, the plots are showing 18S taxa groups along that transect. So it's a way for us to do large transsectional monitoring with autonomous vehicles. So I have a challenge for the user community. Identify the minimum sampling needs by application, which can be distilled to instrument design requirements. So if you want us to build instrumentation for you, you need to figure out what you exactly need, and not a laundry list of things. It needs to be distilled down into manageable 10 wants, basically. And these could be some of those things, like it doesn't have to be submerged. It has a stationary sample location. You want to take 3 samples per day for 30 days. And it needs to have cellular and satellite communications. I think distilling those down into those concrete things are super important. And man, you guys are seeing everything before I get to it. So this box is showing you guys everything that scientists generally come to us and say that they want. We really need you to distill that down into a much smaller box of requirements for development. And to use Susie's bright spot example, I will use the ReadyNet project as a bright spot. This was a fit-for-purpose instrument design, and we were able to iterate really quickly on developing an instrument for the ReadyNet program based on having direct feedback from the end users. So we got the USGS folks in a room and did a Moscow analysis, which is must have, could have, should have, or will not have. And out of, I don't know, 10,000 stickies that I went through on my desk to basically a concrete list of a dozen things that they really wanted that it needed to have. And there was some give and take back and forth with them on what was really important and what wasn't important, but we were able to iterate over the last couple of years to have a beta prototype that we're producing in our lab right now. And so this just goes to show that design requirements, concrete example, or concrete design requirements will enable us to produce faster instruments and make them to what you guys want. So just with some concluding thoughts, there's lots of instrumentation in development, but very few of those are commercialized. And developers need to balance scientific curiosity and novel developments with routine monitoring needs. And then there's knowledge gaps to address interfacing between instrumentation and then standard instrumentation validation and reporting. And the end user community really needs to distill their wants to concrete needs, leading to requirements or ways that we can use those requirements to overlap with specific use cases. And then I just want to finish up acknowledging the Marine Omics Technology and Instrumentation Workshop participants that have been integral in helping draft this review that we're working on, and then our funding and supporting groups that helped with organizing the conference. So with that, hopefully I stayed close to 10 minutes.